Okay, thank you, Boris. The title is very overambitious, so I just thought it was funny. Okay, so maybe before I get started, just a little bit. So I kind of used to be like a deep learning theorist, and I've kind of drifted towards the more kind of engineering side of things over time. So actually, the thing that we've been working on in the last year and a half is essentially trying to design like a new model for language modeling, specifically trying to make like language models based on recurrences rather than self-attention. So we had this nice paper earlier this year on these two models, Hawk and Griffin, which in the bottom left, you see kind of the classic scaling plot, where basically these are models based around recurrences that are getting scaling performance close to the performance of a transformer baseline, which is obviously very exciting. So I could have talked about this, but I felt like, I don't know, people always talk about what they're doing, and then sometimes a lot of the kind of background context of the work is missed. So I thought it might be more interesting if instead I gave like a general introduction to kind of the key concepts about how to train models at scale, and especially like the things that I think are worth knowing, even if you never intend to train a model at scale, but you just want to know like what are the constraints like on my work for somebody else to be able to take it and make use of it. So that's kind of the inspiration. I also like have no idea how long the talk is, so it might be way too short, it might be way too long, who knows? I mean, obviously we'll stop early if it's too long. The rough outline, I'll give like a brief introduction to transformers, just in case some people aren't familiar. And then briefly I'll talk about why actually it's MLPs and not self-attention that kind of dominate the computational cost of training an LLM. Then maybe the most shocking part of the talk, I'm going to try and give like a simple mental model of like how TPUs, which is like the computational units we use at Google, actually operate, like how operations are performed, which is pretty close to how GPUs work, so it should overlap for anybody not using TPU, but also obviously I know TPU better. Then I'm going to talk about how you train a model that's so large you can't fit it in memory on a single device. I'll say just a few words about like what scaling plots look like in practice as opposed to in theory. And then if there's time, I'll also describe how inference as opposed to training works. So a bit ambitious. OK, so let's jump in. OK, so what is a transformer? Like the most important thing I would say to emphasize about transformers is that everybody fixates on self-attention, but self-attention is not the most important part of the transformer architecture. So the most important part of a transformer is this kind of like overall structure that I've plotted on the left, whereby you have this like alternating pattern of some unit that mixes information across the sequence, followed by some unit that mixes information across the different like hidden channels. And then like in order to make this trainable, we always place skip connections around these two units, and then we always place some kind of normalization layer onto each of these branches. So I'm not going to describe why the combination of skip connections and normalization layers makes this network trainable, but this is kind of a thing that's sort of well-known in literature, and I added these on the bottom right because I was appalled to discover that Boris hasn't told his own students that he figured out part of why this works. So there's the paper if anyone's interested. So yeah, this is kind of the key to transformers, is this alternating simple pattern. OK, so then let's dive into those two components. So the channel mixing component of a transformer is the MLP. So this is basically like a computational view of MLPs in one slide. So just briefly, obviously, like normally you'd see the kind of classic MLP. In a lot of scaling work nowadays, you'll find that gated MLPs have become a bit more popular just because they seem to perform slightly better. So what that basically means is that you split the signal into two equivalent paths. You apply some operations in each path, and then you have this like multiplicative gate that recombines those two branches, and then the output comes out. Nobody has any idea why this is a good computational unit, but it seems to perform well. Yeah. So I also just like included the size of like the tensor that's going through the layer. So we have an input of like batch size times sequence length times hidden dimension. When we go through these first two linear layers, we typically expand it to some larger dimension ND. And then we have a final linear layer that recontracts back to the original shape. So the thing that like engineers really care about when they see this is they want to count 3 operations which is like how many parameters does this have? How many flops does it perform that I can structure as a matmul? And then how many like non-matmul flops does it have? So like this, like a single block here would have 3 nd squared parameters, which is basically the linear layers. And then we have like on the order of n times batch size, sequence length, hidden dimension squared flops inside the matmuls. And then we have a smaller number of flops, which are like the element-wise flops in the nonlinearity or in the gating. So that's basically MLPs. And then we have self-attention. Okay, I appreciate this is a little bit of a hard to absorb image. But personally, the way that I find it easiest to think about self-attention is just to kind of track the input and output shapes. So I removed the batch size just to make it a bit easier, but we have an input which is like sequence length times hidden dimension d. We pass that through these linear layers, and then at the same time we reshape it into like a 3 tensor where we have like a number of heads n, and then a head dimension dh. Then we're gonna like take the outer product of 2 of those linear layers in this einsum to get the attention matrix of shape sequence length by sequence length. We're going to apply the softmax, and then we're going to combine that attention matrix with the other path to get the output of the correct shape. So that's kind of the operations that happen. So what like computational units do we have inside self-attention? So first of all, we have like 4 linear layers. So that's like 4 d squared parameters, and it's also on the order of batch size, sequence length, d squared flops inside matmuls. Then we have these 2 einsums that like kind of apply the actual self-attention operation. So of course, those don't have any parameters at all, but they do perform some number of matmul flops. And so if you work it out, it turns out they're going to perform batch size times hidden dimension times sequence squared matmul flops. And then finally, we have to apply the softmax and apply some like masking to ensure that the model is causal. So that's going to provide some number of element-wise flops, and also like something the field got wrong for a long time. Like naively, you might think, okay, I need to like create this causal mask that tells me what's in the future and what's in the past. That would be like sequence length by sequence length. I'm going to have to move that onto the device and move it off. So I'd have to do like on the order of sequence length squared memory reads. So flash attention, which got a lot of attention in the last couple of years, is basically showing that actually you can reduce the memory cost of self-attention to being on the order of the sequence length. And that was like a big speed up.
So can I ask, like, so you say you assume number of heads times the dimension of the heads is capital D. Is that just for you the definition of capital D? Or is that like a thing that you put in for some reason?
So like, I guess I just did the lowercase and uppercase don't match across the 2, but so like D is just the model width. And it's just kind of convention that you make the linear layers D to D, and then you do this reshape into heads, but like you keep the overall size the same. There's no reason why you have to do that, but that's like convention.
What's the inside of flash attention that brings down to linear?
So there's like multiple parts to that. I'm slightly cheating here. But for example, if you take the masking, the naive thing to do is to construct a mask of like sequence by sequence and move that onto the device. But like in reality, you can just like tell the device to construct it on the device, if that makes sense. So like you can just say like, you know, like this is the first token, and just move like the location of the first and last token onto the device, and then have the device construct the mask in place. So basically, like early implementations did a lot of unnecessary computation off of the device, and then you had to move more objects on and off than you needed to do. That was a very like flaky explanation, but we can talk more later. Okay, so that was just like a general to set the scene. Was there any like pressing questions at that point? Beautiful. Okay, so first of all, a thing that you'll hear described a lot on Twitter is people saying that, oh my God, like turns out that MLPs are the bottleneck in transformers. Really, I'd say the true answer is that it's linear layers that are the bottleneck. So why is that? So there are like 2 main important things, which is how many parameters the different operations have, and then the second question is how many flops do they perform. So first of all, like we just saw in the last few slides, that essentially like all parameters inside the core of the model are inside linear layers. So then the only significant number of parameters outside of linear layers is the input embedding and the output embedding. So the size of the embeddings will be like twice the vocab size times the model width, whereas like the linear layers are going to scale with both depth and width squared. So as you scale up the model, in the end, of course, the embeddings become free, and then it's basically all inside linear layers. This is not true for small models. So often small models, you could have as many as half of the parameters in the embeddings. And then obviously the more important thing is flops. So we just saw that there are like two dominant sources of flops. So the first is all of the linear layers inside of either self-attention or the MLPs. That's going to scale as this expansion factor n, batch size, sequence length, model width squared. And then there's the self-attention einsums that construct this attention matrix and apply it. And that's going to scale as the batch size, sequence length squared times the hidden dimension d. So first of all, typically this expansion factor is pretty large, so we're kind of intentionally shifting compute cost away from attention and onto the MLPs. But then more fundamentally, like everybody here can see, that like which of these two operations dominates just depends on whether sequence grows faster or slower than model width. And like an empirical finding is to get good performance, we almost always scale the model width much faster than we scale the sequence length. So therefore, like the flops cost of training this model also is just dominated by linear layers in typical cases at scale.
Okay, so can I ask like a theory-centric question?
Yeah.
Like, is that an example of an interesting thing that would be good to have some kind of clarity about? Like, this kind of like how to scale things like the sequence length versus the width of the model versus whatever, at least in any sense of the word, how to scale.
So I think the way I would frame it is like self-attention is like appears a very inefficient way to transmit information across sequences because it's quadratic. The reason that doesn't matter is because it pans out that like MLPs are so flops hungry that kind of regardless of how inefficient you are at processing the sequence, like communicating between channels is always the dominating factor. So like it's neither, I don't know if it's theory or practical, but if we were able to find more efficient versions of MLPs, we would care a lot more about the efficiency of self-attention. Because our MLPs are so like compute hungry, it doesn't matter that self-attention is not very efficient. Okay, so this kind of has a very simple consequence, which was not kind of appreciated by the field for quite a long time, which is given that linear layers will typically dominate both the parameter count and the flops cost of training, it actually really doesn't matter that much most of the time that self-attention is scaling quadratically in the sequence length, at least during training. So there was a lot of work, trying to make linear versions of self-attention. The reason why those didn't take off is because it's not actually that big of a problem in practice, at least for large models. Of course, if you really target very long sequences, this would stop being true. So I'm not saying this is like completely true, but mostly this is why. This is incidentally not the case during inference. If we get time at the end, we'll describe how inference is different. Okay. So now we're going to go to the bit of the talk I'm maybe most nervous about, which is to give you like a simple description of how TPUs, but essentially also GPUs, actually perform your computations. Okay, so this is like a very simple model of TPU. So on the right-hand side, you have your like high bandwidth memory, which is like your main memory where everything lives. There's pretty slow connections between that memory and like the local memory that lives close to the computations. So then you have this local memory, which is like, significantly smaller than the main memory, but lives very close to the actual computations. And that has very fast communication with the computation units. We then have two types of computation units. So we have a unit which is dedicated to matmols, which can do, this is, I think, TPU v5 I took these numbers for, I'm not sure, which can do like on the order of like 100 teraflops per second. And then separate to that matmol unit, you have a separate unit which does vector or element-wise operations, and that has a lot fewer flops. So that can only do something like 4 teraflops. So that's kind of what things look like.
Can I ask, like, what does 120 teraflops mean?
I mean, I used to be a theorist. I don't know if I can answer that better than you.
But I just mean like how much does a forward pass on a big like LLM cost
Oh, right,
in
right.
terms of matmul? Like should I think of this as like 1 forward pass per second or something? Or?
So I don't think I can free will that, but like the important thing is like the relative scale, of how many flops you can do if it's a matmul versus if it's not. Okay, so as I said, so the high bandwidth memory is where parameters and activations live. So like, for example, if you see an OOM, that's because you filled up HBM. So the thing which I didn't appreciate until a couple of years ago is if you want to actually apply a layer to some activations, you don't only move the input activations from high bandwidth memory into the local memory. You have to move both the activations and the parameters of the layer that you want to compute into the local memory. And then once you have managed to get the memory where it needs to be, then if the operation you want to compute is a matmul, you have something on the order of like 30 times more flops per second available to you than if the operation that you want to perform is some kind of element-wise or non-structured computation. Okay, so that's kind of the overall structure. And so when I say that this matmul unit does matmuls, this is kind of the difference between TPUs and GPUs. So on TPU, typically this matmul unit has like a minimal size. So very commonly, the minimum size will be that you can multiply an 8 by 128 matrix by a 128 by 128 matrix. Any matrix bigger than that, you do in like chunks by just moving chunks of it onto the device and off again. And then if any matrix is smaller than that, like doing a matrix smaller than this will take exactly the same amount of time, because all it will do is just pad to zeros to fill up this size and then do the full computation. So that's why you'll see like Google papers almost always like never have operations smaller than 128, is because smaller than 128 doesn't save anything on TPU for like lots of operations. So just to like, this is the main area where things differ on GPU. So GPUs are like a slightly more general model, at least they used to be. And so you can often get away with smaller operations. And like, I'm not an expert, but just so you're aware. This would be bfloat 16. Is that? Okay, so I thought it might be nice just to run through like what happens when you actually just apply a single linear layer to some inputs. So we're just literally just going to compute this linear layer on the right that takes my inputs of batch size, sequence length, and dimension, and then produces an output. So we have our parameters and our input activations both living in our main memory. So we first have to load both of those into local memory. Having loaded them into local memory, we can assume that it's basically instantaneous to move them from local memory in the actual matmul unit. So we put it on the matmul unit, and then we're going to perform the flops. So like just one important aside is like, even if the batch size was 1, we can treat the sequence length as being like, the like parallelized dimension of that matmul. So we perform the flops, and then we're going to read the output activations back. Hopefully that made sense. So like what everybody does whenever you analyze an operation is you just count up the different kinds of operation. So we have, I'm not going to say it all again, but we have some number of reads and writes and some number of matmul flops, and we don't have any flops that can't be done on the matmul unit. So like 2 key facts. You can do memory transfers and flops in parallel. So the matmul unit can be working at the same time as you're moving memory from high bandwidth into local memory. And then a second fact is that roughly speaking, we can perform like something like 256 flops in the matmul unit in the time it would take to move a single float from HBM to local memory. Which if you think about it is like kind of crazy. If I move one number into local memory, I can afford to do 200 operations on that number. And if I do less than 200 operations on that number, it won't speed up like my training at all. So what this ends up meaning is like if you just compare, so like the reads and writes is going to be dominated by d squared, and the matmul flops is like bs d squared. So basically what this means is if like batch size times sequence length is smaller than 256, then the thing that dominates the computation time is actually just moving the parameters of the linear layer into local memory. And the actual like computation of performing the operation is free. So that's what we would call memory bound. And then if the batch size times the sequence length is bigger than 256, we're flops bound in the sense that we move the memory into the device, and then the thing that we wait for is to actually compute the computation. Are there any questions at this point? Because I know that was quite a lot.
Can I ask, like, should I then think that, like, the number of vector and element-wise operations I should imagine doing just to kind of use things should be, like, roughly 30 times smaller than the number of map malls if I just want one cycle to kind of use everything up? So I should make, like, my width, like, 30 times smaller or something like that. Because I'll do, like, BSD operations for, like, just if I wanted to apply a nonlinearity after linear layer, for example, or something.
Yeah, I'll cover that in a sec. So I believe, I don't want to be certain, but I believe that you can't use the matmul unit and the vector unit in parallel. Like those do run one after the other, I think. I'm not certain, but yeah, but I'm going to say a little bit about what happens to nonlinearity in a bit. Okay, I hope this isn't like too intense, but I hope it is. So what does this mean in practice? It means that if you were to plot like the realized flops per second, like how many flops per second the device is doing against basically the sequence length of the model, you end up seeing like curves like this, where it's like increasing linearly up to this kind of critical point where you become flops bound, and then beyond that, it's constant. And generally speaking, our goal will be to try and make as much of the model on the right of this plot as we possibly can. So we're getting as much out of the device as possible. So based on what we talked about earlier, like transformers are really well suited to GPUs and TPUs because they're dominated by these linear layers. And then so long as the sequence length is bigger than 256, which it basically always is, those linear layers are going to be flops bound. And so we're going to be making full use of the computation available on the device. And like the really important thing to say here is like if you're working on model design, the thing you have to really think about is like, can the operations that I'm designing be made efficient within this programming model? Because otherwise, like people aren't going to pick it up. So this is kind of like the constraints that people who design models are under.
So here you are assuming that the memory move is dominated by moving to the parameters of the neural network and not by moving to the activations? Because the number of activations is also proportional to fetch size, right?
It's not that I'm assuming it. It's that so we have the full thing at the top. So the total reads writes is like the activations, which have to move both onto the device and off. So that's 2 BSD, and then plus d squared for the parameters. The thing is like because the matmul flops is like BSD squared, like that's kind of always hidden. So like when BS is small, d squared dominates. And if BS is large, then we're already flops bound, if that makes sense. We can talk more afterwards as well. Yeah?
As you get new TPU versions, is the 256 kind of moving like to the right or left?
Yeah, that's a great question. So obviously, like all numbers here should be taken as like rough senses of scale. So yeah, like the boundary is not exactly 256, and it moves around from device to device. And like a pain point sometimes being at Google is that like models which are efficient on TPU will not be the same as not exactly the same as models that are efficient on GPU. So like if we optimize a model for our hardware and then like you try to like get the open source community to use it, like they're not going to get the same performance because they're working on different devices. Okay. So yeah, hopefully this gave you like just like a general sense of how computation works. So this kind of gets back to Boris's question. So now obviously a real model is composed of like multiple operations that happen like one at a time. And so some of those operations are flops bound, but some operations will be memory bound. So for example, we just showed you that this linear layer is typically flops bound. But then we're going to apply this nonlinearity. And it's pretty clear the nonlinearity is memory bound because basically like I'm performing on the order of 1 flop per read from memory. So like the nonlinearity is super memory bound. So what we can do is we can basically fuse operations together. So basically what ends up happening is the device, rather than computing the linear layer and the nonlinearity separately, it's told to compute the linear layer, then immediately apply the nonlinearity before you read the output off of device into the main memory. And of course, what that means is you eliminate this like unnecessary step of reading memory off and on of the device between two operations which have output and input that are the same. Does that makes sense. So like this is called fusion, at least at Google. So this happens in two ways. So first of all, this happens automatically. So for example, if you're using JAX, when you use jax.jit, like this is basically what jax.jit is doing, is it's like telling the compiler to look for operations that can be fused. And that will then speed up your computation by like concealing these memory-bound ops in adjacent flops-bound ops. But of course, like your compiler won't find the optimal fusion most of the time. And so it's becoming increasingly common for people to actually just hand code these fusions by writing custom kernels. So that would be like in Palos or CUDA or Triton. So like explicitly telling the device exactly how to run the operations and exactly when to move memory around. And we're kind of getting to the point where you actually can't make a model competitive with state of the art without writing custom kernels for your new model. Like it's becoming kind of like a core skill, which is intense. OK, how are we doing for time? Oh, we're good. So that was like a brief introduction to how devices actually work. So now obviously another big question would be, OK, like I'm scaling up my model. Obviously at some point, like, I told you that the parameters have to live inside the high bandwidth memory. So at some model scale, which is typically around 7 billion parameters, you simply can't fit the model parameters into HBM. So then obviously the question is, well, what do I do? So probably the first scheme that emerged is pipelining, which I think is the thing that people would probably guess. So in pipelining, basically you put the parameters of layer 1 on device 1, the parameters of layer 2 on device 2, the parameters of layer 3 on device 3. So then the inputs come in, you send them to device 1, the outputs go to device 2, and it goes up, and then it comes back. So obviously, conceptually, this is very simple, and it's pretty easy to code up. But the big issue is that you can see there's a lot of wasted compute. Because after layer 1 is finished, it then has to hang around waiting for layers 2 and 3 to terminate before it can then finish the backward step. You end up, especially as the model gets deeper and deeper, with a lot of wasted computation.
Can I ask, like, is that a reason to use bigger batch sizes? 'Cause I would have thought, like, like as long as they can kind of keep feeding things to layer 1 or more elements in their batch, maybe it's not like just sitting there as long or something like that.
Yeah, so that's actually a good question. So one way around the wasted compute here is to use some kind of asynchronous training, where you feed multiple batches through, and it's not like you don't perform the update on batch 1 and then perform batch 2. You start them before the first update has been complete. So that's one option. And then your problem is, OK, I have to make asynchronous training work. So people tried to do that for a while, and maybe that could work. But what's more common nowadays, at least this is definitely more common at Google, and I think it's generally just more common everywhere, is instead of pipelining, we'll do sharding. So what that means is rather than putting an entire layer on a device, we're going to put some fraction of every layer of the model onto device 1, and then we'll put the remaining part on device 2 or 3 or whatever. So each device is storing some part of the parameters from every single layer in the model. So obviously the advantage here is every device is always working all of the time. But now the big mystery is, OK, communication between different devices is going to be very slow. So how can we do this in such a way that we minimize how often we have to communicate between different devices? So that's kind of why it wasn't obvious to people that this scheme on the right could work. So the solution is actually really nice and really clean. It's called Megatron sharding. It came from this paper at the bottom. And the idea is kind of shown in this slide. So imagine that we want to shard a single MLP. So I just plotted on the left, but we're just going to focus on the right-hand path of the MLP. So we're going to apply a linear layer, then we're going to apply this gating operation, and then we're going to apply a second linear layer. So what I'm going to do with Megatron sharding is the first linear layer, so this is the bottom on the right-hand side, I'm going to split it across the rows of the matrix. So the top half by rows of the matrix will go on one device, and the bottom half will go on a second device. Whereas the output linear layer, I'm going to split it by columns rather than by rows. So why is this a good idea? If you just imagine the input propagating through this model, So when I apply the first linear layer at the bottom, because I've sharded it by rows, like basically device 1 gets exactly half of the intermediate activations H, and device 2 gets the other half. And crucially, both H1 and H2 are like exactly correct. Like no communication is required. Like that is the first half of the output. So now because I have the exact like hidden activations H just split across 2 devices, now I can apply like any element-wise operations I like. And because the element is already exact, like that's not going to create any communication. So I can apply this, this multiplicative gate, and then I'm going to get the like sort of updated hidden activations H prime. Now I'm going to apply the second linear layer, which has been sharded by the columns. And now I'm going to get out 2 outputs, Y1 and Y2. So Y1 and Y2 are kind of like partial, you know, like the true output Y is the sum of Y1 and Y2. So the key idea here is I'm able to like compute this MLP, and I only have to communicate once. So I go through the 2 linear layers, and then I do a single all reduce where I communicate the values across all of the devices. But I've only had to do a single communication step, and that comes out to be like the best that you can achieve. Yeah.
Is there a way to do this with 3 layers? No, right?
Great question. So like this ends up imposing some constraints on model design. The constraints is basically no one's going to take seriously a model which has odd numbers of dense layers, because you're going to do an unnecessary communication step. So people only ever use even numbers of dense layers, and basically they only ever use 2. And then any other operation that happens between those 2 dense layers either has to be element-wise, or if not element-wise, it has to be block sparse, meaning that it like, you know, it like lives entirely within like H1 or H2, and it doesn't create communication across the 2. And so these are kind of like if you have a design at the small scale you want people to take seriously, like this is like one of the rules that you have to obey.
So you like can't put a normalization layer in.
So normalization is fine because that like is effectively element-wise. Because normalization, you're going to normalize like
Like you can't put let's say layer norm, for example, where you have to know the scale of all of the like blue and greens or something like that, right? To normalize them. Maybe you could just do it on both halves or something, but then it won't be exact.
Yeah, you would either, I guess you would do it before across all, or if you did it like within, then you would do it on like the component, like you do it on half. But like, yeah, I guess people would just do it before and then you do it on all of it. Okay, so just like a few like other kind of minor considerations. So this was all kind of focused on the parameters. Obviously, there's also the optimizer state. So obviously, if you think about Atom, like it's tracking multiple moving averages, so actually the optimizer state is larger than the parameters themselves. But like the simple solution is we just co-locate optimizer state with the parameters. So we just like only store optimization state, you know, next to where the parameter lives, and then that kind of solves that. There's one other like concept that's, you know, maybe worth vaguely knowing about, which is rematerialization. So, you know, when you run backprop, that's generally going to require you to store like every intermediate hidden activation, so that then you can perform the backward pass. But like one thing you can do if you're just kind of slightly shorter memory is you can trade memory for flops by discarding most of those hidden activations and only storing, like say, like every n layers, you store the hidden activations. And then in the backward pass, you just repeatedly recompute the missing components. So this is kind of like a last resort trick if you like have a deadline and you just need to get it to fit and train, like just to save like a little bit. There's like one place where rematerialization is actually a really good idea, which is if you have like a model where there's some part of the model that's actually dominated by memory bound ops rather than by flops bound ops, then obviously because it's a memory bound op, the flops are basically free. So like there's no reason not to do this. So actually like Mamba is an example of a model which like where the design explicitly relies on rematerialization to make the backward pass work. And if you didn't have remat, then the backward pass would be really slow. So like there are like edge cases where there's actually isn't.
Okay, can I just ask? Can you just clarify again what 1B means? What exactly does it mean to co-locate them?
I just mean like, you know, we said, okay, we're going to shard, like each device stores some fraction of every layer. So we're only going to put, like we're going to shard the optimizer state in exactly the same way. Okay, how are we doing? Okay, so now the closest we get to like actual science. So of course, I think everyone here kind of knows about scaling laws. So the idea is you have typically a plot of validation loss against like total compute, so flops. Obviously, the cheat is we put both on a log scale, and as everybody knows, most plots are straight on a log scale. And kind of the key idea is this idea that you get like predictable improvement in the validation loss as you scale the training budget. And then in addition, the hope is like, we do some tuning at the small scale, we find some better data set, a better model, or better hyperparameters or something. And like we anticipate that basically will just like shift this scaling curve down. So like we do some research, we improve things, and then we get this kind of global improvement in performance at any flop scale. That's kind of what we want to see. So like one nice example where this is exactly what happened is kind of the trajectory from GPT-3 to Chinchilla. So like a design decision that was made in GPT-3 was they basically scaled like the size of the model, like the number of flops the model performs in a single update, while using like a fixed budget of training tokens for all model sizes. So then there was this like a work at DeepMind from a few years ago, Chinchilla, where they basically explored, okay, what's the trade-off of like model flops versus like training tokens? And basically they found like a very intuitive optimal scheme, which is instead of doing that, you should scale training tokens and model flops at the same rate. So basically, if you give me 4 times more flops, I'm going to double the data set and double the model size. And you see like exactly this phenomenon that just the whole curve shifts down. So sometimes things are this nice. But unfortunately, like I'd say most of the time, this is what scaling plots actually end up looking like. So you have your nice straight line, everything looks great. You convince your company to allow you to do a really big run. And then like, one of your larger runs is just like way off of the expected performance. So you extrapolate out to some scale, everything is great, and then it kind of like goes haywire. So some possible reasons why this might happen is like there might be some training instability, which is kind of mild at the small scale, but becomes critical as the model gets bigger. There might be some really important hyperparameter that you incorrectly like figured out how it extrapolates. So it was kind of set well at the small scale, but then like it becomes poorly set as the model gets larger. And there's like an infinite number of reasons like why these things might occur. But like this happens a lot in practice. And so like, just as an aside, like I would say I don't know anyone who sets off like a truly large scale run and expects the final model to lie exactly on their scaling curve. So I wouldn't say we really have predictable improvement with scale. Like one of the biggest uses of scaling plots is actually like it allows you to tell if your performance is underachieving what you would hope to achieve. So like if you see a kink like this, it's like a strong indication that you've made a mistake. And then you go back and you analyze the model, you figure out what the mistake was, and then you rerun. That's kind of like actually why I think they're really useful. And then obviously kind of back to that point of like why that happens. Like if this is a really big model, we can only afford to train this once. But of course, there's like 100 hyperparameters inside of this model. And if we get like a key hyperparameter wrong, that's going to like get us to go from green to red, and that like could be a catastrophe for the company. Yeah.
So the most famous case of a big model landing on the curve is claimed was GPT-4, right? Where they extrapolate up really big, or maybe it was GPT-3. Where like they make huge extrapolation and say, oh, it's bang on the line. Do you think that actually they like messed up a bunch of times and eventually got it on the line, or do you think actually?
I can't know. Like as I said, like both happen. Like sometimes everything is dandy and it works out, but obviously like it's a classic survivor bias. Like people only publish scaling curves that are straight. So like yeah, there's a decent chance that like there were some experiments that went wrong like during the research phase. Yeah.
What do you mean by afford here? Is it afford in like an organizational sense? Like there's other people's demands and the time for the H100s or whatnot? Or is it like, the electricity bills are killing you?
Well, just obviously like your boss isn't happy if like you like set off like a $10 million+ training run and you get a rubbish model. Like, yeah. I mean, yeah. I mean, I was being vague, but yeah. Okay, so like, yeah, we have this huge space of hyperparameters, and we can't figure out, it's not easy to figure out which ones matter. So in reality, like, we don't only have scaling plots of like loss versus flops, we basically end up with scaling plots of like every hyperparameter that we think is important against flops in order to be able to extrapolate these hyperparameters. So it kind of explodes into this huge space. And so I just wanted to do an aside, like this is actually a place where theory can really, really help. Because obviously like experiments become more and more expensive with scale, but theory is like fixed price. So like some nice examples of this is like, MuP at least claims to kind of find the relationship between learning rate and model width. So that's like taking one important hyperparameter away from the things that you have to determine experimentally. A nice example that's less well known is this paper by Sadiqa Maladi on like figuring out like the scaling rules of Adam, which kind of just like figures out the relationship between batch size, learning rate, and beta 2, so that you can kind of merge them into like a single key hyperparameter that you have to tune. So like these kind of like theoretical results that tell you how different hyperparameters relate and like which ones will be important and which like how they'll scale, like are like super valuable. Like, just an aside.
Before you go on, can I just ask, like, do you think there are other reasons you might get a kink, like in the sense that, you're bound with some model and you're going to scale up the flops, for example, just by having more data or something like that, and you have so much more data than your capacity of the model that you're just on a different kind of like. Part of your scaling law at all. Like it's still a scaling law with a different exponent, but you're just no longer doing things in an optimal way in terms of being compute optimal or something.
Yeah. I mean, there's like a huge number of reasons why it can go wrong, and like these are like the two that will happen first. But yeah, there's a lot of reasons why it can go wrong.
Well, I guess if you go to a huge scale, then if you need more data, then that additional data will also be of lower quality.
It was the subject of
data you could get.
the talk yesterday, wasn't it? The afternoon session about how these things might happen.
I thought you couldn't make that talk, although I want to watch it back. But like data degrading with scale would be a classic reason why this might start to go wrong. Or like, you hit the scale where you have to repeat your data set because you've like trained on the full data set, and then you'll see a kink, for example. Any other questions? Okay, I think this is actually going to pan out, if Boris will allow me like 10 minutes, this will pan out perfectly, but we can also call it a day here. Okay, sweet. Okay, so I thought finally it'd be nice to talk about like kind of the computational aspects of running inference, because this is actually the one area where transformers are not good. So it's kind of the area where it's possible to beat them. So just as a reminder from earlier in the talk, like the kind of one of the key parts about devices is this like compute versus memory bound kind of competition. And like computationally, basically transformers are just like a bunch of linear layers. And so during training, like these are always flop bound because the sequence length is always long. And so you always get like really good device utilization. But this kind of nice property of transformers completely breaks during inference. So like, how does inference work? So inference is like typically divided into two stages. So like they have different names. For example, typically we might call it prefill and decode. So in prefill, like the user gives us like a complete prompt, which might be like, what is the capital of France? And because we receive the whole prompt in one go, we're able to parallelize across the sequence length of the prompt. And so long as the prompt is like on the order of 200 tokens, which it almost always will be, like prefill basically looks like training. Like everything is flops bound because we were able to parallelize across the prompt. But then when we want to decode, so we want to produce the capital of France is Paris, like this is now order regressive. So we're producing tokens one at a time. So if you think about it, the sequence length is effectively one. Like at every step, we only have one token that we're able to compute. And so because of that, we're like heavily memory bound. And so as a consequence, like, we can pre-process the prompt something like 10 to 30 times faster than we can generate the actual sample. So there's like a big difference between the speed of prefill and decode. So one of the nice things is there's an incredibly simple model of the speed of the decode step. So as I said, we can, so long as the batch size is small, because that would be another way we could become flops bound. But if the batch size is small, then we're definitely memory bound. So what that means is like the time required to produce the next token in the sequence is literally just like how long does it, like how many things are there that have to move from HBM memory into local memory, divided by how fast does stuff move from HBM memory to local memory. And that completely summarizes the speed. So then that you quickly work out that like the time it takes to sample a token is just like the number of parameters plus the batch size times the cache size, which is like how much information the model has stored about the sequence, divided by this memory bandwidth. Hoping that made sense. And what I want to say is like this simple model is like very accurate, like numerically accurate. And if your decoding is like slower than this equation by more than like a small factor, that tells you that your code is performing like redundant memory swaps. Like it's unnecessarily moving information back and forth between the two memories. Okay, so just briefly for those who like aren't familiar, like what is this cache that I mentioned? So here's the kind of attention diagram from earlier. And so these like this first einsum is basically like comparing, like producing this outer product of like between the queries at our current time step and the keys across all of the previous time steps. And then when we apply the second einsum, again, we're basically using this attention matrix to look across like all previous values as well. So what that means is like we only need the queries at the current time step, but we need the keys and the values for like all previous time steps in order to run inference. And obviously, we don't want to have to keep recomputing these keys and values. So instead, all we do is we just put them in a cache, and then we just retrieve them when we need them. So what's like the size of this cache? Well, it's going to be the depth of the model times the size of the outputs of k and v. So that's just going to be twice the sequence length times the model width, since I told you that like the like head dimension times the head width is always going to be the model width. So the key thing here, of course, is that this cache is going to scale linearly in how long the sequence is. So as the sequences get longer, this cache is going to get bigger. Okay, so one like nice trick that like really helps is multi-query attention. So previously, like k and v, like both produced like an output of size model width, which we then broke down into like some number of heads n times some like head width dh. So multi-query attention is like a super simple idea where we just only bother to have a single head for both k and v, but we keep like a full n heads for the queries q. And if you think about it, like you still end up with like n like attention matrices. Like despite the fact that you've made k and v significantly smaller. But the consequence is that we've made much smaller the operations which have to go in the cache. So this makes the cache like maybe 10 to 30 times smaller. The thing that's surprising, which I can't explain, is that this doesn't actually harm performance very much. So it turns out you can make the transformer cache a lot smaller for not too much cost. And just like an aside, like there are many other tricks people use to reduce the cache size of attention, the most obvious being local attention, where you just only look across some fixed window, but then there are others as well. Any questions? Sweet. Okay, so why do we want to reduce the cache? So obviously, one reason that you'd want to reduce the cache is to like, in terms of the speed of sampling in this first equation. So if the cache size is smaller, the time to sample the next token is going to be smaller. But actually, the main reason we want to reduce the size of the cache is if you think about like how big can the batch size be during inference. Of course, like the maximum batch size that can fit on the device is just the size of memory minus the number of parameters. So that's like everything apart from cache that I have to store, divided by the size of the cache. So like the smaller the cache, the bigger the batch size I can fit in the same amount of memory. And then the reason that it's really nice to increase the batch size is that because like inference is memory bound, so like the added flops you perform when you make the batch size twice as big are completely free. Like they don't cost you anything. So then generally like when people evaluate inference, they tend to look at two metrics. So the first metric is latency, which is like how long does it take to sample a sequence of length n? And that would be at some like fixed batch size, i.e. 1. And the other metric people look at is throughput, which is like if I was allowed to use whichever batch size I wanted, like how many total tokens per second can I generate out of this chip? And those are kind of the QT metrics. So latency is intuitively completely dominated by the kind of the first equation that I showed you. And that's kind of shown in this plot. So basically, this plot is the only plot I had of latency, which is why it's a bit weird. But so the multi-query attention plot is a transformer that uses multi-query attention. And then Hawk and Griffin is like from our own work with recurrent models, where like the big contribution of recurrent models is that the cache is much smaller. So basically, you can think of green and orange as just another language model with a much smaller cache. So what you will basically always see is if the number of tokens you want to generate is pretty small, then the cache is small. And as a result, you're just dominated by how many parameters the model has. And then as a result, like all models have the same latency. So long as they're the same size, they have the same latency because it's only parameters that matter. But then as you grow the size of the sequence, a model which has an inefficient cache, like the size of the cache will start to be competitive with the number of parameters, and that's where you start to see differences. So you get this kind of classic transition from like parameter bound to cache bound as the sequence grows. Does that make sense? But you can probably see like here, so this is, we went a lot of work to make these kind of models with a smaller cache. But actually, like unless you like are decoding like 4,000 tokens, like you're getting like pretty marginal wins. So it pans out it's actually pretty hard to get significant wins in terms of latency. But the place where you can really beat transformers is throughput. So this is a plot of the same models, but instead plotting like what's the throughput we can achieve if we independently set the batch size for every model. And you can see that like, you know, these two models which have both like a smaller cache, but also a cache that doesn't grow as the sequence length grows, end up having like much higher total throughput than the transformer, which also will get like lower and lower throughput as the sequence grows because the cache is getting bigger, and that's forcing the batch size to be smaller. You know, so the dominant factor in why the throughput is so much higher is just that if you can fit a bigger batch size on the device, then you basically amortize the cost of loading the parameters because that cost is shared across all of the different elements in the batch. And like that then gives you a big win. So like, yeah, that's basically how it pans out. Okay, this is actually, I think, the final slide. So the only caveat on everything I just said, so this is kind of analyzing like the autoregressive part of sampling. But of course, like an empirical thing is like, actually for lots of practical applications, the prompts might anyway be like orders of magnitude longer than the generation, especially if you just want to like analyze a massive set of documents and then produce like a yes/no answer, for example. So even though prefill is like 10 to 30 times faster per token, there are applications where prefill still dominates the total inference time. So it's kind of like case by case whether the autoregressive part is actually a limiting step. Okay. So that was everything. I hope that wasn't too overwhelming. And how did we do? Oh, not bad. So great. Yeah, thank you so much. And I'm happy to take any questions.